Hello and welcome to this video about matrix proofs. In this video we'll prove these four statements about the trace of a matrix. The first involves addition, the second involves the transpose of a matrix, the third is about multiplication, and the fourth is about similar matrices. So the trace is the sum of all of the diagonal entries of a matrix. It's usually always only done on square matrices. And this is the definition using a sum and symbol. And the entry has two subscripts the same because it's referring to entries in the diagonal. This seems like a simple function and like it shouldn't have all these properties. So we'll start with the first part of this theorem, which looks obvious, but we'll prove it anyway. We'll expand it out into ijth entry notation because it works so well for so many proofs. Then we'll use the definition of trace, which uses sigma sum notation. You can see how it adds all of the entries up in the diagonal together. Then we can bring everything into the same sigma sum. We can then pack it up again into the trace function of a matrix in ijth entry notation. And then finally we can write in the variable names of these matrices, thereby completing the proof of part A. Now to prove part B, which is also obvious because the transpose function leaves the diagonal of a matrix unchanged. We'll start with the left-hand side and expand it out into ijth entry notation. We'll evaluate the transpose function, thereby swapping the indices of the entry in the square brackets. Then we'll apply the definition of the trace function and use the sigma sum symbol. We could have just as easily have used j as the dummy variable, but it's only a dummy variable, so we'll use I straight away. And we can pack it up into the trace function while returning the subscripts flipped. And then finally we can write it out with its variable name, which has no transpose indice next to it, thereby completing the proof of part B. Now to prove this harder statement, that the trace of a product of matrices doesn't depend on the order of multiplication. So now to start this proof, we'll rewrite these matrices in ijth entry notation. Then we'll bring these entries into the same square brackets using the rules for multiplication, which uses a sigma sum and a dummy variable k. And we can expand it out again using the definition of trace, and so we'll get this double sigma sum. Then we can get rid of the brackets because there isn't a dependency of these variables on each other to require them. We can swap the sigma sums, putting the sigma sum with k on the outside. Then we can swap the dummy variables I and k. This will cause the sigma sums to be swapped again. I'll just scroll the screen up so as to make more room to write more stuff. Then we can swap the a and b variables around, which we can do because it doesn't affect the sum. We can put these brackets around the sum again, getting it ready to transform it back into ijth entry notation. So then we'll rewrite this sum in ijth entry notation, with the variables a and b swapped around. We can then separate these variables into separate expressions inside two sets of square brackets, using the rule for multiplication in reverse. And then finally we can write the matrices using their variable names, thereby completing the proof, because these matrices have been shown to be swapped around inside the trace function. Now to prove this seemingly hard proof, but it'll be easy because we'll just use part C of this proof to prove it. So now to prove it, we'll put brackets around the last two matrices so we can treat this expression like it's the product of two matrices. Then we can swap these expressions around using the part of this theorem that we've just proven a while ago in this video. Then we'll use associativity to swap the brackets like this so as to enclose this pair of inverse matrices. And then finally, this pair of matrices will become the identity matrix and get cancelled out, thereby proving this last part of the theorem. Notice that we didn't need to expand these matrices in any way. We only needed to use past theorems to manipulate them. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.